Everybody can hear me? 어, 잘 들리신, 예. I will start the lecture at 10:33. I will wait the students coming for 3 minutes. You can see the collab screen, right? Yes, thank you. I will wait the student for 2 minutes. Okay, let's start the lecture. Today's lecture is about generative adversarial network. Okay. So, hello, this is TA Yansu, and let's start the practical session. Before start the practical session, please download all the materials. All the materials in the LMS, this IPython file and two Python files, FID bar score.py and inception.py. Okay, I hope everybody download these files, and our goal is to understand the fundamental components of a GAN and implement simple vanilla GAN. Also, in this practice session, we will cover noise sampling and GAN laws. By the end of the session, you will have a working knowledge of how GAN work and hands-on experience in training one. Okay. So first, check your GPU setup. I use A100 GPU in the car lab. And like the last practical session, import all the packages. I think these packages are familiar to us because we use a lot in the practical sessions. And let's create a folder. And these folders we will use later. And preliminary step 2 is define visualization and image saving codes. But in this practical session, I will do not cover this code in preliminary step 2 code because it's just matplot library. So just run the code, please, like this. And preliminarily, step 3 is load dataset and define the data loader. Um, in this code, we also use this MNIST dataset, which is very familiar to us. In class, due to time constraint, we just use MNIST, but there is the other dataset like Cipher10 or Fashion MNIST and extras. So if you're interested to implement SCAN or other practical sessions interest, you can use Cipher10 or other dataset by yourself. But in this class, we just used MNIST for due to the time constraint. So let's download the dataset, MNIST dataset. Okay, I hope everyone follow up this code. And let's move on to today's main topic. Define your generator and discriminator. First, let's define the generator and discriminator with MLP layer because we haven't covered CNN yet. So understand inner working of generator and discriminator. It will be crucial to completing this task. You should be clear about input and output component for a generator. The input will be the noise image, and output should be the generated image. And for discriminator, the input should be the image, and the output should be some logic. Um, so in this practical session, you have to generate your own generator and discriminator here. I will give you 10 minutes and you implement your own generator and discriminator. After 10 minutes, let's check together. Let's get started. Okay, let's check the answer. I'll show you answer. Um, okay. Let's see the generator first. Yeah, we define the main architecture of our generator. The goal is to transform input noise vector into the image-like structure. The generator's role is to take in random noise and map it to a data distribution that looks like our target data. In this case, 28 by 28 grayscale image, which could represent something like handwrite digits, which we are using the MNIST data set. So first, the linear layer, the generator takes in a random noise vector of size 100. The noise is our starting point to generate the data that will eventually look like a real image. The layer map the 100 dimension to 256. And next we have two hidden layer and with 256 neurons, and they both use the ReLU activation functions. The ReLU activation function introduce non-linearity, which is important for learning complex data pattern. So, and the sequence, and then the final, and then the linear 256 to 256, they follow, and then the ReLU, is repeated, which is our learning complex transformation of our input noise vector. Okay, and we do this because we are learning complex transformation of our input noise vector, gradually shaping it to resemble real data. And finally, final layer maps 256 neurons to 784, which is the flattened size of 28 by 28 grayscale image. This is because we want to produce an image-like structure as an output. And we do the sigmoid activation function to ensure each pixel value in our generated image is between 0 and 1, which is standard for normalized image data. It effectively squash each output value into this range. And let's see the forward function here. First, the output equals self.main input. The input noise is fed through the network defined the self.main. This means it goes through all layers just we discussed and transform the input noise vector into the 784 dimension output. And we do the output.view here. Since our final output is currently 784 dimension vector because of here, and we need to reshape it into form as image. So the view method reshapes the output into the batch of 28 by 28 image, and 1 represents the number of channels grayscale, and -1 means placeholder that PyTorch to automatically infer the correct batch size. Okay, this is the code of generator code, and let's see the discriminator model. Okay, now that we covered the generator, let's move on discriminator. Remember, the role of discriminator is to act like a binary classifier. So it takes an image, either real or generated by generator, and determines whether the image is real or fake. Let's read the code step by step. Discriminator receive an image the size of 28 by 28. This is done because our network is fully connected layer and we need to work with one-dimensional data. So we transform into 256 features. And in this time, we will use nn.liquilelu. You can also use Liquilelu in generator here too, but why we use Liquilelu here? Because the network includes 2 hidden layers, but 256 neurons after. Sorry, but why we use Liquilelu instead of Relu? Because it allows small non-zero gradients when the input is negative. This prevents dying relu problem, so we use liquid relu, and the last linear layer reduce. Okay, I will mute all participants. Okay, let's see the code together. The last layer reduce 256 feature to a single output value, which represents the probability of the input image being real. And finally, we use sigmoid activation function to constrain this output to a value between 0 and 1. effectively making it a probability score. The value closer to 1 indicates that the discriminator thinks the image is real, and closer to 0 indicates it's fake. And lastly, the discriminator is forward function. Here, the input to the discriminator is originally in the shape of batch, 1, 28 by 28, representing a batch of grayscale image. Since we are using fully connected layers, we need to flatten them into the vectors like this. And we pass the flattened input into the network we define in the self-domain. This output will be a probability between 0 and 1, indicating whether the discriminator believes the input is real or fake. And the discriminator output initially shaped to the batch size comma 1. However, we want to cover it to the shape of like this. So we use the squeeze dimension equal 1 function to remove this extra dimension. So we end up a one-dimensional tensor containing the probability score for each image in the vector. So this is the for discriminator function. And upload the GPU. Okay. Your next task is implement noise sampling function. You can use torch.rand, which sample values from the normal distribution. Ensure the noise size is set to batch size and noise dimension. So what is the answer here? Do you know it? The answer should be like torch rand and this one would be the answer. Okay. So let's move on the training session here. Okay, I think everyone follow this code, I think. Okay, let's move on the training again. As you know that discriminator and generator have conflicting goal, the discriminator are correctly classified between real and generated samples, and while generator's goal is confused discriminator. Also, discriminators seek to maximize the objective function, whereas the generator looks to minimize it. However, based on our Tuesday session, we will make a slight adjustment to generator's objective to ensure stability during training, which means we do not minimize the objective function. We are trying to maximize the likelihood the discriminator making errors. So I will give you 10 minutes to implement this code, and let's see the answer. So I will give you 10 minutes to implement this code. Okay, let's check the answer here. Okay. So let's walk through our GAN training loop here. And we are going to cover the two main steps of training, updating the discriminator and updating generator. The goal is to teach both network to play the adversarial game, where the generator gets better at creating realistic data and the discriminator improve at distinguish real from fake. So first, a label's answer would be like this. We create a label tensor of ones because we are training on real image where label one represents real, and the output we pass the data through the netv to get output the discriminator's prediction for the real data. The error between the discriminator prediction and the real label is calculated using this criterion, and we also do the output.mean.item this code because this mean of discriminators predictions on real data used for monitoring training progress. And next is let's train with the fake data. We generate random noise size, flat size, 100. And the generator creates the fake data from the noise. So the pass the noise to the netg. And we create the label tensor of 0 to represent that the data at the one it represent the data is the fake. And we pass it through the netd and calculate the error between the discriminator's prediction and the fake labels. And we also do the mean to the output. This mean discriminator's predictions on fake data useful for monitoring the training progress. And do the loss backward to combine the real and the fake one. Fake loss to calculate the total discriminator's loss. Then we back propagate to calculate the gradients and update the discriminator parameter using optimizer d.step. Okay, let's update the G network here. Here we are use 1 because from the perspective generator, the goal is to make the fake data look real. We pass the generated fake data through the discriminator to get its prediction, and the generated loss is calculated as how well it can fool the discriminator into the predicting one for a fake one. Then you do the same like this to after the generator's update. And you can save the image in the here, and you can save the checkpoint to this code. And you can see here, you can see the loss function of the ng here. Like this. So this is the training. As you implement this code, you can you can do the next step. You can see like loss function like this. Okay, I will just stop and let's visualize and generate it, the image. You can visualize like this one. Okay. We define some visualization function, plot bar GIF in at the beginning of our practical session by running this code as the beginning. Okay, as the beginning of the training, the generated image is unclear and we don't know what is this meaning and it's just see like noise. But after the training goes on, like you can see like this, I think there is so many one, but you can see like this is more clear and can be written compared to the first image. This is like noise sample. We can recognize it. We cannot recognize from this image, visualize image, but we can visualize what is this like. This is 9, this is 8, this is 1. Okay. So this is the visualization code. And let's do our last practical session's last topic. Evaluate your model with FID score. I think everybody follow here. I think. But I will give you 2 minutes to see the answer of the training code. After 2 minutes, I will move on the next chapter, the FID score. This is the this fixed noise is the same as this noise sampling code here. So the code for the beginning of the fixed noise is the random noise sampling here code. So this is because the GAN's input is a noise image, noise sample. So we use this like this and I will give you 1 minute more to see this code. Okay, let's move to the FID score. Okay, evaluating the generated model is challenge like unlike classification tasks where the correctness of the result can be directly measured against the label. Determining the quality of image produced by a generative model isn't straightforward, so various metrics have been proposed to address this challenge. But today, we just focus on French inception distance score, with what is called FID score. So in the course, we will handle this FID score and okay. Okay, what is the FID score? FID works by extracting feature from both real and fake data set using the inception network, which is neural network pre-trained on ImageNet. It then calculates the mean and covariance of these extracted features and measures the distance between two distributions. In the graph shown here, we see example of image with a varying level of disturbance, and how that affects FID score. Okay. As the disturbance increase, the meaning the image become more distorted and less realistic, the FID scores also increase. This indicates that generated images are moving further away from real image distribution, which is reflected the higher FID score. A lower FID score means that generated images are closer to the real image and thus higher quality. FID is commonly used metric in GAN research because it provides the qualitative way to assess similarity between the distribution of real and generated image. It is widely preferred because it captures both the visual quality and diversity of generated images. One important thing to note is that the inception network using FID calculations is pre-trained on ImageNet, which is not aligned well with another data like MNIST. This could make FID score for dataset like MNIST is less reliable. But in summary, FID score helps us to evaluate how close our generated images are to real ones by measuring the distance between their feature distribution in a pre-trained network. The lower the FID score, the better quality of generated image as you see in this figure graph. So, okay. If you want to see more about this, you can see by this article or paper here. And you can, for the implementation, you can see the GitHub here to see the code of FID score in PyTorch. Okay, we do not cover this code and how codes very detailed in this practical session. And we just import this FID score Python file and inception Python file in this lecture. This file is I give to you, so your code file must contain this two Python file. If you don't have, you will maybe get the error code. So let's evaluate your model like this. And let's see the code. Okay, let's walk through the code that is used to calculate FID score, which evaluate the quality of the image generated by GAN compared to the real image from the MNIST dataset. So here, we load the MNIST data using torch vision and the dataset.mnist, we set train equal false because we are loading just test set. The transform equal transform to tensor converts the image into the tensor, which is need to fit into the our model. Next, we create a data loader for the test data. The batch size 50 means we will load 50 images at a time and shuffle through, ensure that images are randomly shuffled each iteration. We also use num_work2 to parallelize the data loading. This loop extracts the first batch of real image from the data loader. Real data set will contain 50 real MNIST images from the tested data set. We only need one batch, so we break out the loop after the first iteration. And now we generate a batch of fake image using generator model NetG. First, we create the random noise vector of size 50 by 100, which produces a batch of 50 fake images that attempt to look like real MNIST digits. So this is the explanation of the code. And here we save the image to the disk. The disk is we make the prior code here. And let's evaluate the FID score. Okay, this is the FID score. You can see it. The output FID value gives the FID score like this, which quantities the difference between the real and generated image. The lower score means the fake image is more similar to real one, and the high score is not good image, which is far from the real image. So this you can see, you can calculate the FID value with this code like this. I think this session is almost finished because we do not cover the DC again today's lecture because this is the additional session. So in your home or when you have some time, I hope you guys study and implement DC again by yourself. And in this session, we do not cover DC again. So I think this is the end of the class. I will wait 5 more minutes. If you don't have any question, you can go out. And if you have any question, and stay here 5 more minutes, and I will I will answer your questions. Okay. I will finish the lecture. In GANs, the tangent H activation function is commonly used in output layer. And this produces a value range of -1 to 1, which helps normalize data and stabilize the training process. So the last of generator, we use tangent H activation function. Mm. Oh, okay. I will show you training part of GAN here. I think I do so fast. Sorry for that. Can you see the code? In the end of class, I will upload the solution file so you can see the solution file too, but this is the training part of the GAN. You guys have any other question? I will wait for 2 minutes. Did you don't have any questions? I will end up this Zoom. Is there? Oh, there's what I do is dx is the code for this is used why we use this code because this means the discriminator's prediction on the real data used for monitoring it and training progress. And I also do DG bar Z1 because this this is also useful for monitoring progress, monitoring the training progress. So for monitoring training progress, I use for the saving DX, DG, Z1, and DG, Z2. I think that this is the answer for the questions. Okay, do you have other questions? I think everybody solved their questions, so I will the end of the Zoom, and you can see the solution file from LMS at end of the class. So thank you.